All right, we're going to go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover getting started with wolfSSL, part 2 of our two-part webinar series, presented by Engineering Manager Chris Conlon. My name is Emma, and I will be moderating this webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Chris will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 60 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2 TPM 2.0, a secure bootloader known as WolfBoot, Java wrappers and JSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now I'd like to turn it over to Chris to discuss getting started with wolfSSL in 2026, part 2.
Thanks, Emma, and hello everyone again. Like Emma said, my name is Chris Conlon, Engineering Manager here at wolfSSL. Today we're going to go into part 2 of our Getting Started series. You can see on this slide here what we plan to cover today. Last week we went over more of an introductory start to wolfSSL with the package structure, how you build it, how you test it, and some of the basic usage from a client and server perspective. Today we're going to move on to a few more in-depth things. We're going to talk about how to configure the library, some tips on porting it to embedded systems or just different platforms in general, a few notes about our OpenSSL compatibility layer, talk about DTLS and PSK usage, session resumption, and then a few notes on debugging and some of the typical common problems we see getting started. Hopefully we'll have time for some questions at the end. We've got a lot of content here for you today, so hopefully you can find this useful for starting off your year. So last week we mentioned how you build wolfSSL using AutoConf on Linux, Unix platforms. You're typically using configure, make, install. And the problem that a lot of users face getting off the starting line is that we have a lot of configure options to choose from. We have over 380 configure options now in wolfSSL for things like enabling features, disabling features, customizing algorithms, and different parts of the protocol, which is good for customizability and helping it meet your needs, but also can be a little bit daunting getting started. We're going to go over just a couple of kind of the common ones here. There's not really a best top 10 that apply to everyone. So hopefully some of these can apply to you and maybe other use cases. We do have an enable all option. So if you want to enable all the features we have in one option, go ahead and throw that in there. It's good for development and testing. We use that in a lot of our internal tests. It's just to make sure we have all the features turned on for doing, things like static analysis or something like that. Enable TLS 1.3 turns on TLS 1.3 support, latest protocol version. That is on by default. We talked a little bit about debugging with enable debug. That turns on our debugging logging layer. If you're only a crypto-only user, we have enable crypt-only. So they'll disable and compile out all the SSL and TLS layer code. It can be useful if you're trying to minimize the library footprint or just reduce the attack surface of the library if you're not using the TLS layer. We have an OpenSSL compatibility layer, so enable OpenSSL Extra and enable OpenSSL All. Extra is a subset of the whole compatibility layer, kind of the most common used subset. So that's a good place to start with. OpenSSL All will enable all of our OpenSSL compatibility layer APIs. So if you don't find what you're looking for in Extra, you can bump up to All. If you're on Intel and AMD platforms, here's some options that can help with performance. Enable AES-NI turns on our AES-NI assembly performance speedups. So this will give you kind of the maximum AES performance on Intel and AMD processors that support that, which includes pretty much all the modern ones today. Enable Intel ASM. It also enables AES-NI, but also turns on our other Intel specific performance improvements. There's other Intel intrinsics like AVX that accelerate SHA. And so that's kind of a catch-all enable option to just enable all the assembly for Intel AMD type platforms. We do have different assembly. So for example, enable ARM ASM is kind of the same purpose. If you're on an ARM platform, that'll turn on all of our available ARM assembly. I linked to our blog here that covers some of those different assembly options if you're curious about that after the presentation. If you're doing key generation, we have enabled keygen. And if you're doing certificate generation for X509 v3 certs, we have enabled certgen. One feature we have inside of wolfSSL is called the crypto callbacks. So enable crypto CB will enable that. This is an option that allows you to write a crypto callback, essentially what it sounds like, that calls down to different algorithms, and you can choose where you're calling down into that. So for example, if wolfcrypt or wolfSSL wants to do AES, CBC will call the crypto callback you register with us and allow you to do that operation in somewhere other than wolfcrypt software crypto. So you might be calling down into an HSM or a TPM or hard rail accelerator, or maybe a different library that you have available. Enable alt cert chains. This is a common one that comes up in our support tickets. So this one will commonly help out real world certificate chain validation if you're running into problems there. And what it does is only require the leaf certificate loaded into wolfSSL and then tries to dynamically build up the trust chain from the leaf cert to the CA dynamically. Some memory configuration options. Enable static memory. This will enable our static memory only build. So it pre-allocates all memory in a collection of memory arrays in a memory pool. And there's some options you can do to configure the different sizes of those buckets. A lot of times this is going to be needed if you're in a safety critical use case or need deterministic memory behavior. Enable track memory. This is going to report memory on cleanup about some stats on what memory was used. So it's helpful if you want to see how much memory your application was using at the wolfSSL level. It's kind of helpful if you want to try and memory leaks. You can see where things are initialized or allocated, and then when things are freed. Enable distro is the option we use for our distribution packages. So, things like Debian and Ubuntu type distributions. And if you want to configure with the same options that we use there, go ahead and turn this on. Enable single threaded gets rid of all of our threading and mutex code. This one can be helpful if you're on an embedded or bare metal platform that doesn't have threading support. Or maybe you're just trying to simplify your build if you're not in a multi-threaded use case. A few options that talk about resource constrained configurations. Enable small stack. So this build's goal is to use at most 1 kilobyte of stack space and push the rest to dynamic memory with malloc free. We of course have users that are in different categories of memory use. Some want, all stack space, all stack usage and no heap usage. Some want all heap usage and no stack usage. So this is just one of the options that we have to help you configure for some of those goals. Enable small stack cache. This caches large stack allocations on the heap and can help you reduce peak stack usage. Enable lean PSK. This is the smallest build we've ever done to date of wolfSSL. It was a pre-shared key PSK only build. The footprint size came in at 21 kilobytes. So it is a very minimal build, probably just for a subset of use cases, but as a reference point there. Enable low resource. This turns on a number of things. The goal of it's to just kind of get down resource usage in general to help you save RAM or flash space. So there's some notes there about what this does disable. So session cache, it turns on our RSA low memory feature, uh, the small builds of some of our algorithms like Curve and Ed 25519, some of the AES modes like AES GCM, etc. So TLS uses a session cache for session resumption. By default, this is sized to 33 sessions, but you've got some options to control that. We have enable small cache, which lowers that down to 6 sessions if you're on an embedded target. And essentially the session cache is going to be used to store session keying material. And if you overflow the size, it's going to start overriding existing entries. So just keep that in mind, I guess, as far as gauging how many active sessions you have going on. Enable big cache increases the cache size to 20,027. Enable huge cache and increases it to 65,791. And we do have another option called Titan cache, which is even higher than that. A couple build options to adjust for TLS 1.3 handshake variants. Enable post auth. In TLS 1.3, you can optionally do authentication post handshake. So enabling this allows use of some APIs we have to do that. Enable early data enables TLS 1.30 round trip time or zero RTT mode, where you can send early data up front with the first client hello. That's sometimes not generally useful, but if you've got a protocol or a specification that knows how to use that early data, then it can be useful in those cases. So those are some of the top kind of common ones. Of course, you can always run the -- help option for configure and see the full list. And we do try to document what things mean in our wolfSSL manual. As always, if those aren't clear, those descriptions aren't clear, feel free to email us and we can give you some more details on those. Cross-compiling, this is a common activity for a lot of our users, especially ones that are compiling down to embedded targets. wolfSSL does support that through configure. You'll need to use the -- host variable, and you may also need to specify some things like your compiler, your linker through the available variables that configure offers. In addition to those, you might need to specify some like compiler linker options depending on your platform that you're compiling to. Here's just kind of a common configure line that we have seen used in the past. You can see the M CPU specifies the name of the target, ARM processor, -M thumb compiles for ARM thumb mode, -OS optimizes for size. The spec settings enable semi-hosting. And we can always help you get some of those right too if you run into some problems. By default, when you run make install, we're going to install to user local. And if you want to install wolfSSL to a different location, you can use the -- prefix option. So then whenever you run make install, we're going to install wolfSSL and the header files to the directory you specify with that prefix. So we covered some configure options. Next up, let's talk about some things specific to porting to embedded systems. Oftentimes there's a lot of challenges when you're porting C code down to an embedded system. Your embedded systems might have small memory spaces. You're definitely not on a desktop type operating system. It might be bare metal even. Your processor's running slower, so you might have to worry about performance. Sometimes you don't have things like file system or standard logging capabilities, and different compilers behave a little bit differently. Sometimes you've got different standard libraries than commonly you'd find in like your Unix type environments. So wolfSSL tries to help you with those things by allowing you to exclude algorithms, shrink down the build sizes, change to different math libraries to help you fit into your available memory resources. We've abstracted out things for platform dependencies. We can leverage hardware cryptography if your processor's slow, but you've got a faster crypto coprocessor. And we've tested with a lot of different compilers. So hopefully we're just going to support yours out of the box. We really tried, since the beginning when wolfSSL was founded to design it with portability in mind. So that should help. And you'll see in the next couple slides of how we've done that. we'll cover some abstraction layers that we have around, the C standard library, locking, logging, custom IO, and some OS level things. So first off, the C standard library, we'll go through memory handlers, string functions, character handling, math functions, and file system. The first of these being memory handlers. Normally, you're just using malloc, realloc, and free. A lot of platforms have a different equivalent of those, or maybe you've got your own memory handlers you want to tie into. So wolfSSL abstracts these out to xmalloc, xrealloc, and xfree. So these are things that you can define to your equivalents, either in your user settings file or inside of our porting layer. If you define xmalloc underscore user, then you can put these defines inside of your own user settings.h header. So this is where you would define them to your own like custom malloc implementation, or maybe you have a different named function there. You can also register memory handlers at runtime. So if you don't want to do it at compile time through those previous defines, you can call wolfSSL set allocators. And then we have callback functions for malloc free and realloc, which we'll essentially call every time we want to, malloc memory or release memory or reallocate memory. The callback prototypes are defined in our memory.h header. So this just shows you kind of what you should expect there as far as writing your own callback. From those parameters that we saw on this slide, there's a void heap pointer. So this is a heap hint. If your application wants to use a custom heap instead of the default one, you can pass that in and use that inside your callback. There's a type argument that's an integer, and that's useful either for us internally, for like our static memory build. This is kind of a hint as to what kind of memory bucket we pick. You can also use that inside of your memory callbacks as far as helping you choose where to allocate the specific memory being allocated from. So if wolfSSL is, allocating an input buffer, then that type will be set to dynamic type in buffer. If it's allocating an SSL structure, it'll be dynamic type SSL. String functions, wolfSSL uses string.h by default, so your standard memcopy, memset, etc. We do abstract these to xmemcopy, xmemset, and xmemcompare. Like the memory functions we saw earlier, you can define a define called string underscore user, and then provide defines of these to your custom equivalents. And this is the full list of our abstracted string functions right now. So any of these could be mapped over when you define string user. For character handling, we use ctype.h for things like 2-upper, 2-lower, and is alpha. By default, we'll, again, abstract them to their X equivalents. By defining ctype underscore user, you can map those handlers to your own implementations. And for math functions, for Diffie-Hellman operations, which you may or may not be using depending on your algorithm set, we do use pow and log from math.h. And so if you're using those, we abstracted those to xpow and xlog. If you're not using Diffie-Hellman, you don't have to worry about providing these. So if you did want to override those, you would define user underscore math underscore lib. For file system, by default, we're going to kind of assume your standard file system exists to load and process things like certificates and keys. If you don't have a file system, you can just completely disable it by defining no underscore file system. And that will expose, or I should say, they're already exposed. That disables the file system equivalents, but you can use the buffer equivalents. So you'll have functions that allow you to read a certificate in through a C array or a key in through a C array. So that's just kind of reiterating what I said. We can use files or loading things in through buffers or C arrays. Here's an example, the first one there of loading in a CA certificate from a file. And then the second example there is loading it in through a buffer using the wolfSSL CTX load verify buffer. When we covered that in part 1 of the Getting Started webinar as well, the last argument there represents a format, which is going to indicate to us if that's in PEM format or DIR ASN1 format. For time, wolfSSL does require an accurate system time, but we'll use time.h by default. And we use this for validating certificates and certificate chains since they have the not before, not after ranges in there that need to be validated. We have several methods or ways of overriding this depending on what you have available on your platform. Kind of the first, the biggest thing would just be, hey, let's just disable complete all of the time code in wolfSSL. You can define no ASN time and it'll do that. The downside of this is that it's also going to disable your date verification checks. So we don't really recommend you do this if you have some other way of getting an accurate time source. One defined, we have user underscore time. This will use our internal GM time implementation and time structures. And then you just have to provide a function that returns the seconds since the Unix epoch. So you can define X time to your custom time function. The next option we have is time underscore overrides. This will allow you to override both X time or I should say time and GM time with our X time and XGM time macros. The XGM time essentially just will convert or expect you to convert a time t to a struct pointer. For threading and locking, by default, wolfSSL is going to use mutexes for locking in multi-threaded environments. If you don't have, mutex support, or you're not in a threaded operation in your application, go ahead and define single-threaded, and that'll compile out all of our use case for those. For logging, we did talk about how you can enable debug logging with enable debug. You can also define debug underscore wolfSSL. And then at runtime, you can call wolfSSL debugging on to turn on debug logs and wolfSSL debugging off to turn off debugging logs. And that's really helpful for seeing what's going on and troubleshooting. By default, with this logging mechanism, wolfSSL uses fprintf and puts things into standard error. This isn't applicable for every use case. You might want to put these somewhere else. So you can customize this by registering a logging callback. If you wanted to do that, you would call wolfSSL underscore set logging CB. That would take in your logging callback. You can see it's prototyped by that second line there, which essentially you're going to get a log level and a log message where you can print that wherever you want. You can find different log levels in our logging.h header. And this might be useful for different use cases. You might not have standard error or fprintf available. You might want to push log messages into a log file, for consumption, or maybe you need to transfer that off your device to look at. If you don't have any file system or terminal available, you can use this to push things across like an Ethernet or a serial connection. We've done that several different times. Custom IO, this is a pretty popular one for our user base. So by default, wolfSSL is going to use a BSD socket API for input and output. So, whenever we want to send data, we call send, and whenever we receive it, we call the receive function. A lot of our users don't have the BSD socket API available, or they want to have a kind of a higher control over where they're sending and receiving data from. Imagine, you might want to do TLS over a serial line. We have users who've done TLS just over memory buffers, or maybe have a custom or proprietary transport protocol. And so it allows you to essentially do SSL and TLS over anything as long as you can transfer data. To turn this on, you'll define wolfSSL underscore user underscore IO when compiling wolfSSL, and then you'll need to define two callback functions, one for sending and one for receiving. They're prototyped in our wolfio.h header by these prototypes here. So you'll have a callback IO receive and a callback IO send. Whenever wolfSSL wants to send data, we'll handle all the encryption, and then we'll just give your send callback an encrypted character byte array, and then you can just send that however you want. And then likewise, whenever wolfSSL needs to receive data, we'll call the receive callback. Off the wire, you can just get the encrypted data and hand it back to us through that callback, and wolfSSL will handle decrypting the raw stream there and then hand it back to your application through normal SSL read calls. You can register these callback functions using wolfSSL set IO receive and wolfSSL set IO send. This is at the context level, which is wolfSSL CTX. An optional per wolfSSL session user context can be set. So this is essentially just a kind of a pointer to anything that you need to get back inside of your callbacks that you might need to help you do IO. So that might be a pointer to a structure where you're saving memory buffers. It might be a pointer to like, some kind of TCP/IP structure that you need, or really can be anything you want. See, the context pointer here is just showing you'll get that back as the last argument in your callbacks. For operating system ports, we've already ported wolfSSL to a lot of operating systems. It's most likely that we already support your OS. We ported to 50 plus operating systems, which includes RTOSs down to bare metal. If you look in our wolfSSL wolfcrypt settings.h header, you can oftentimes see a lot of our port layers for operating systems. So when we port to something like FreeRTOS, we'll just add a define called FreeRTOS. So when you're building wolfSSL for that OS, you just have to define that, and that just switches over the whole OS level, port. So here you can see FreeRTOS, SafeRTOS, ThreadX, Micrium, MicroCOS, an iPhone build, etc. And the same concept applies to TCP/IP stacks. So when we port to one, we'll offer you a defined for an easy enablement. So if you're on LWIP or LWIP, you can just define wolfSSL LWIP. That switches our IO layer internally over to calling their API instead of our normal standard socket API. We do support the LWIP native APIs as well as their BSD API. So have LWIP native uses their native component of that. We've done NetX, Pico TCP, and a few others. And then just a reminder, all these things can be put into a user settings.h header. So that's kind of our intention, is for you to have and maintain that header from release to release of wolfSSL, where you can put all of your customization for wolfSSL in there. And it's just one singular spot instead of trying to, put those defines a bunch of other places. When you define wolfSSL underscore user settings, wolfSSL automatically looks for and tries to include your user settings.h just from the include path that's been set. I did mention it in part one of our Getting Started webinar too, but we have some example user settings under the examples configs directory. We have one for all, one for minimum ECC build. The wolfboot key tools is one that we use with our wolfboot tools build that just kind of includes a subset of algorithms there. You can use user settings with configure autoconf. If you use the -- enable - user settings configure option, it'll look for a user settings.h file, which you can just put right in the root wolfSSL directory. If you're doing that, you'll have to disable the examples since they're assuming, more of your standard desktop type environment by default. Our OpenSSL compatibility layer, oftentimes we have people migrating from OpenSSL to wolfSSL, and this includes a subset of the OpenSSL APIs that gives you the same header prototype, and then internally we map that down to wolfSSL logic. So it just kind of eases your effort involved in migrating from OpenSSL to wolfSSL. That's the benefit. The downside is it does enable more functions inside the library, so it can increase the footprint size a little bit. So if you are on like an extremely resource constrained device, it may be worth evaluating just using the native wolfSSL API instead of turning this layer on. It wraps more than 500 commonly used OpenSSL functions. It is an incomplete wrapper because OpenSSL itself has over 4,000 functions. It turns out, usually most of those don't need to be used in a standard TLS connection. So it's likely you'll just fit inside of our existing compatibility layer as far as your use case goes. It is not uncommon for us to run into gaps, and we can easily fill in missing gaps from this layer if you need. You can enable this like we saw earlier with enable OpenSSL extra, or you can define OpenSSL underscore extra. The header files for this layer are in the wolfSSL /OpenSSH, OpenSSL header directory. For example, wolfSSL slash OpenSSL slash SSL.h is the main SSL level header. That's just some examples of things you might see in that header. You can see how we define, an OpenSSL function name gets kind of mapped over to a wolfSSL equivalent, and then that's implemented internally inside of our library. So if you're porting an application over using this, you'll have to add the wolfSSL subdirectory. Well, I guess one option is to add the wolfSSL include subdirectory to your include path, so your application can continue to include things like OpenSSL slash SSL.h. The other option is not to add that wolfSSL subdirectory to your include path and then adjust your includes to have a wolfSSL slash prefix in front of them. And then once you've got the header and the include path figured out, you'll just need to switch your link time from linking against OpenSSL, which is -LSSL -L crypto, over to linking against wolfSSL with -L wolfSSL. In the perfect scenario, that just compiles and works. We've done this with a number of things, LID, STunnel, OpenSSH, Nginx. We have a repository called the OSP. So wolfSSL on GitHub. If you go to github.com/wolfSSL/OSP, they'll show you some of the patches we have for these projects. DTLS and PSK. So DTLS is datagram TLS. This is designed to be run over unreliable protocols like UDP. So, like if you think of like VoIP type applications or something like that, it has to kind of build up all the reliability things that UDP lacks, because TLS itself still requires, to receive your handshake messages and whatnot in order. So it has retry mechanisms built in and things like that. For building wolfSSL with DTLS, we have enabled DTLS. It's disabled by default. And then we've got some options that allow you to configure that for setting the MTU size, enabling DTLS 1.3, and enabling DTLS connection ID support. We saw in part one of our webinar how you would use a protocol function to create a new wolfSSL context. Here you can see the DTLS equivalents of this for DTLS 1, 1.2, and 1.3. There's a wolfSSL DTLS function that's used to determine if the session has been configured to use DTLS. A DTLS get peer function, which gets the sock adder in structure of that DTLS peer. DTLS set peer is kind of the equivalent opposite operation, which allows you to set the DTLS peer as far as the sock adder in structure goes. Set timeout max, that's the maximum DTLS timeout. That's going to be used for things like retransmission of drop messages. wolfSSL DTLS get current timeout returns the current timeout value that you're at. wolfSSL DTLS got timeout. So this is something your application calls. If your code thinks you've reached a timeout, it'll kind of force a retransmission of the last messages that were sent. For examples, you can look at our example client and server that supports DTLS out of the box. You can also look in our wolfSSL examples GitHub repository, and that has examples, of several different variants of DTLS client and servers. If you're using our example client server, you can use the -u. That'll switch over to using DTLS. And then this is a little snippet of what you might see coming out of I think this is the server side. If you look in our wolfSSL examples repository, just that server-dtls.c is just kind of a minimal server that uses blocking IO. Probably a good starting point if you're just kind of getting going with DTLS. There's a non-blocking example, which means it's using non-blocking IO, server DTLS non-blocking.c. That's a good example of how you might use timeouts with a non-blocking IO infrastructure. There's a client, DTLS shared.c. This is an example of how you might access the same wolfSSL object from multiple threads. So there's a mutex in there that prevents access of that object from more than one thread at once. The next category of kind of handshake variants is PSK, or pre-shared keys. This is where you pre-distribute keys to the client and server. And the differences are that you're not going to be using X509 certificates anymore. So it can help reduce the complexity of your handshake. It can help reduce the algorithms and ASN code needed there. And it oftentimes it's faster. So if you remember to our smallest build that we ever did was a lean PSK build. That was the same PSK as we're talking about here. For pre-shared key cipher suites, we have static PSK suites disabled by default. So that's ones that don't support perfect forward secrecy. If you do need those back, you can always define wolfSSL underscore static underscore PSK. If you want to turn off pre-shared key completely in your build, you can define no underscore PSK. And then just like our non-PSK protocol variants, you can set the cipher suite list using wolfSSL CTX set cipher list. So with PSK, you're going to use callbacks, a client PSK callback and a server PSK callback. And these are going to be used to kind of tell wolfSSL about the pre-shared key used for that connection. And you can set your client and or server callback either at the wolfSSL session level or the wolfSSL CTX context level. This is what your client callback is going to look like as far as the callback prototype goes. There's a hint. So this is coming into your callback as an optional server hint that can help your client pick the correct key. A lot of times you might be storing your keys in like a database or something and need some kind of key to look that up. The identity is an output variable, the client identity. So this is going to be sent to your server to help the server pick the correct key. The ID max line is the maximum length of your identity. The key is obviously your pre-shared key, which is an output, variable from your callback back to wolfSSL. And then key max line is the maximum length of your PSK key. You return the actual size of the key that you're putting into the key variable. We have an example client PSK callback in our wolfSSL/test.h header. So that can be a good point. You can just see how we set the key. There we're just setting 4 bytes inside of that key array offset 0, 1, 2, 3. And then like this client side, we have the server side. So it also needs a callback to be registered. It can be registered at either the session level or the context level. And it's prototyped again by something similar. Here's the WC PSK server callback prototype. There's an input argument that's identity. That's the hint that you're going to receive from your client to help you pick the right key. Key is an output argument for you're going to put the key, the pre-shared key. Again, you get a variable representing the maximum key length that wolfSSL supports, and then you'll return the actual bytes as far as length goes of your key. We have an example server callback in wolfSSL test.h as well. Your server can also send the pre-shared key identity hint either at the context or session level by calling one of these APIs. wolfSSL CTX use PSK identity hint or the session equivalent of that. And then the server internally will store the identity to help the client pick the correct key. For identities, wolfSSL supports up to 128 octets. That's the same for hints. And then for pre-shared keys, wolfSSL supports key lengths up to 64 octets. If you want to get your PSK identity back from wolfSSL, you can call wolfSSL get PSK identity. And then if you want to get the PSK identity hint, we have a getter function for that as well. Okay, we're done with our handshake variants. The next kind of big topic that people like to do with TLS is session resumption. So this is going to speed up subsequent or further connections to the same endpoint after your initial one. So it allows you to skip some of the performance intensive public key operations that are used to derive keying material. So it really is helpful if you're planning on reestablishing your connection to the same endpoint. Things like your browser and such will do this automatically behind the scenes. There's a couple ways you can do this. The first one, this is the more historical method, is using session IDs. And this is supported on, of course, both the client and server sides. It uses the session cache that we talked about earlier. So here's just telling you defines again that you can use to control that session cache size. I said if you go past the session cache size, wolfSSL will just start overriding entries in that cache. The biggest cache we have is the Titan session cache, which is just over 2 million sessions. So on the server side, you don't really have to make any changes. The session cache is enabled by default. So if you don't disable it, then you should be good to go. On the client side, you do have to do a couple things to resume a session. So after your first successful connection, so you typically call wolfSSL connect for that, you can get a wolfSSL session structure pointer back by calling wolfSSL get session. And then you'll use that later on to reload that session state back into a wolfSSL structure. So for example, your application goes on, calls wolfSSL new, that makes a new wolfSSL structure. Then you call wolfSSL set session using that same wolfSSL session pointer that you got from wolfSSL get session. And that essentially kind of restores the state back into the wolfSSL structure. After reloading the state with that previous function, you can do your connection again by calling wolfSSL connect. And then the client's going to send the session ID to the server. And if everything is still valid and hasn't expired, the session will be resumed. If you want your client to kind of poll if session resumption was done and the session was reused, you can call wolfSSL session reused, and that'll return 1 if your session has been resumed. Otherwise, it'll return 0. And session resumption isn't a hard failure. If a session fails to resume, it usually just will fall back to a full handshake. Sessions have timeout values. So the default timeout value of a session is 500 seconds. This is kind of the standard specification default. You can override this if you want. You can define wolfSSL underscore session underscore timeout. And when a session does timeout, it just is essentially considered expired. And then the server will just do a new fresh handshake with that client. Some common issues around session resumption. So if your client's not resuming, it could be for a few different reasons. It could be that the session's timed out on the server, so you waited longer than that 500 seconds. Your session cache entry was overwritten. So if your server session cache is too small for the number of clients connecting to it, maybe that your first entry got overwritten before your resumption could come around. The other option is that your server didn't have a good random seed value. So this one isn't always clear, but if you are not running into the first two options, it's something you might want to look at. That check your WC generate seed function inside of wolfrandom.c and just make sure that's actually returning a random value. By default on Linux, we call dev random or dev urandom, but sometimes on embedded platforms, we have ways that users can plug in custom RNG seed methods. So we've seen people, accidentally hard code like the same value every time instead of giving back a random value. So the second method of resuming sessions is using session tickets. This is defined in RFC 4507. And it's a way to resume a session without requiring specific state to be stored on the server. So it can be useful for servers that are handling large numbers of connections because they don't have to store as much state and use as much memory or database space or session cache space. It could be helpful if you want your servers to have session cache entries that live a long time. It can be helpful if you are load balancing requests across servers, since then it's not dependent on that specific server. And then it can also be helpful for embedded servers just because you're alleviating some of the memory usage there in the session cache. It's essentially a mechanism to distribute an encrypted session state in the form of a ticket back to the client. The ticket's created and encrypted by the server and then sent back to the client during the handshake. And then the client presents that ticket back to the server to resume the session. For wolfSSL usage, we have an enable option to turn that on called enable session ticket. You can also define have TLS extensions and then have session ticket, since it is a TLS extension itself. At runtime, you enable that either at the session level or the context level using one of these functions. For getting and setting a session ticket, so this could be used, say, on your client side. You could call wolfSSL get session ticket. That would give you your ticket back. And then kind of like we resume sessions, where we got the state and then set the state again, you'd set your session ticket by calling wolfSSL set session ticket. We have a session ticket callback you can use. So this would be called when a session ticket is received by the server. You can see it's prototyped by that callback session ticket line in the middle of this slide. You essentially get the ticket and the ticket size and an optional user context. We have a ticket encryption callback. So this would be used on the server side where you could register this if you want to take control of the encryption of a session ticket. We do have a default ticket callback implemented inside of wolfSSL, but this is for users that want to have a little bit more control over that. I think I mentioned a few times there's a hint. This is included in the new session ticket, which is kind of a new handshake message, as a hint to the client of how long the ticket should be stored. So the client can abide by that. It's more of a recommendation. 0 indicates the lifetime's unspecified. And then there's a few other options there as well. So TLS 1.3 switched completely over to using session tickets for resumption. There was some middle box compatibility that maintained the session IDs being in there, but really it's just using session tickets for resumption. Okay, so what about debugging and some common errors that we see? I did talk about debugging before. I'm just going to mention it again because it is very helpful in figuring out problems. If you enable debug, you'll get something that looks like this. Really, like I said, it's just giving you more context around an error. And if you contact our support team, we'll probably ask you for a debug log just to help us see what you're also seeing. We have some more debug options, which we didn't talk about last week. There's a wolfSSL underscore debug underscore TLS define. And so when you define this, it's going to add in more data to that log. So you're going to see data being sent and received as far as hex data goes. You'll see extension data as far as TLS extensions. And you'll also see some of the public key material showing up in that log. You can imagine this is going to expand your log quite significantly in size. We have a define called show secrets. So what this does is print out some of the client and server random values into your debug log. This should really only be used for debugging and not in a production environment, since this can be used to decrypt your session traffic. We have an wolfSSL underscore keylog file defined. You can also enable this using the --enable -keylog -export configure option. And when this is enabled, it's going to create a file and write to it called sslkeylog.log. And what you would use this as for is Wireshark has a way you can use this to set the pre-master secret logging callback or logging file, excuse me. And then Wireshark will be able to decrypt your encrypted traffic. Like, for example, it's helpful if you're trying to debug TLS 1.3, since more of the handshake messages are encrypted, including the certificate message. So if you want to use this option, you can kind of decrypt that and inspect some of that traffic. Again, really don't use this in production ever. Just this is only a debugging, troubleshooting type step. Some common issues. So we see a lot of things come up in our support team. These are just some of the more common ones we see. So -323 and -327, this is a want read or a want write error. You'll typically see this if wolfSSL read or wolfSSL write fails. And it's not a true error. What it means is that, when wolfSSL read tries to read from your underlying IO, if there's no data available there, it will return want read, which just means, have your application loop around and try the call again when data is available. You'll probably see this more times, when you're using non-blocking IO, since the underlying IO is meant to be non-blocking and will return similar type error codes. Bad version, -326. So this can be seen if you're trying to connect like different protocol versions together. Cannot match cipher suite is -501. So that means your client has a list of cipher suites it's trying to use, that is incompatible from the server Cipher Suite support. So you might need to, look up what your server supports as far as Cipher Suite goes and readjust your client settings. No signer certificate. This is a really common one, negative 188. So, TLS clients will try to verify the certificate chain of the server during the handshake. And if you don't have the right CA certificates loaded, you'll see this negative 188 error show up. So that means that you need to go out and find the correct CA certificate to load for your connection. Sometimes it's a little unclear where that comes from. A lot of times, say like native wolfSSL might hit a load balancer instead of following that back to an end server. So, oftentimes Wireshark can be pretty helpful to see the peer certificate chain that you're actually connecting to and seeing. And then the last one there, negative 308, this is a socket error, which is just a general socket error. Typically, we see this on the client side, and it means the server, shut down this underlying socket. And so that typically is indicative of a problem on the server side that the server encountered, and it just didn't send back an alert. It just decided to, shut down the connection. So there we would recommend go back and look at if you've got server logs, that would be the best case. A couple quick resources. We mentioned a few of these on our webinar last week. The wolfSSL manual is very informative. We do try to put things in there, and it gets updated every night based on a Jenkins job that we have run. So it really is kind of bleeding edge documentation. The wolfSSL porting guide covers a lot of the things we covered today as far as porting to an embedded system goes. The wolfSSL GitHub repository, that's where you're going to find all of our latest source code. If you need to open issues or open pull requests, you can do that there. Our YouTube channel is really helpful. All these webinars we put up on YouTube, so that can be a great knowledge base to go and learn about different things from our wolfSSL experts. And then lastly, the best resource if you really get stuck is just email our support team at support@wolfSSL.com. We offer free pre-sales support, so we can help you get up and running and building and everything before you go any further than our pre-sales level. So that brings us to the end of our part 2 of our Getting Started webinar. Thanks again, everyone, and I'll open it up for any questions.
Awesome. Thank you, Chris. To start the questions, if I'm porting an application over to use wolfSSL instead of OpenSSL, should I use the OpenSSL compatibility layer or your Wolf provider product?
Yeah, that's a good question. So if you're migrating from OpenSSL to wolfSSL, there's really two main ways you can do it. Our OpenSSL compatibility layer is a set of APIs. So in this regard, you're going to be completely switching to OpenSSL, potentially not having to change your application code too much. The second solution path we have is one we didn't talk about too much today, but we call it Wolf Engine or Wolf Provider. And this is actually a provider that plugs in underneath OpenSSL. So you can use Wolf cryptography underneath OpenSSL's SSL and TLS layer. And that's usually a good solution if you've got a lot of applications using OpenSSL and you want a validated version of cryptography underneath for things like FIPS or ACVP, CAVP, or common criteria or something like that.
Wonderful. What is the best way to add new hardware cryptography support to wolfSSL?
Yeah, if you have a platform that has hardware crypto that we haven't supported yet, usually that can be added fairly easily following our existing patterns. So, you could follow our existing patterns and add a port layer in yourself inside of wolfcrypt. We have a wolfcrypt source port directory to put, hardware specific files and code. The other option, which is probably more user-friendly if you're going to do it yourself, is to write crypto callbacks like we talked about. And so that would offload all the crypto or cryptography that we do into your callback, and you could use that to call into your own hardware crypto. But we can always do the porting for you too. It typically takes us, a week to a few weeks, depending on the complexity of the hardware platform.
Wonderful. Does wolfSSL support assembly optimizations for RISC-V?
We do. So for RISC-V, wolfSSL supported building on that platform for a number of years now. We do have assembly-specific optimization inside of our math library for RISC-V. So that would be equivalent to the stuff we have for x86, x86-64, MIPS, RISC, etc. So that should accelerate your performance of wolfSSL on RISC-V platforms.
Wonderful. Well, thank you, Chris, for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfssl.com. Thank you again, and we look forward to seeing you on January 21st for our webinar on getting started with wolfSSH in 2026. Thank you all.